A polynomial Px is given by the term a0 x raised to n plus a1 x raised to n minus 1 plus a2 x raised to n minus 2 and so on till an, where n is a positive integer and a0, a1 till an are constants. It is important to note here that when we get a term like 1 over 2x plus 3, because we won't have a positive integer n for those values for x, um, those will not be thought of as being polynomials. Now, a polynomial of degree 1 is called a linear polynomial and it is of the form ax plus b. And a polynomial of degree 2 is called a quadratic polynomial, which is ax squared plus bx plus c. And a polynomial of degree 3 is called a cubic polynomial, which goes as ax cubed plus bx squared plus cx plus d. And an example being 2x cubed plus 5x squared minus 7x plus 10. However, it is important to note that when we say a polynomial is, say, of degree 2, what we mean there is the highest power of x in that equation, which is a positive integer. And remember, if x is raised to a power which is not positive integer, then it is not considered to be a polynomial. Now, let's understand what we mean by a zero of a polynomial. A real number k is said to be a zero of a polynomial p of x if we replace x by k so that we have p of k and that equals 0. For example, if we are given a cubic polynomial x cubed plus x squared plus x minus 3 and we put for x the value 1 and then we get 1 plus 1 plus 1 minus 3 which is equal to 0. And therefore, since in this case p of k is equal to 0, k being 1 in this case, we say that 1 is a 0 of the polynomial px. In fact, as a general rule, it is important to remember that number of zeros in a polynomial of any degree n is at utmost n. Let's take a simple example. If one zero of the polynomial px equals x squared plus kx minus 5 is 1, we have to find k. So since we know that the 1 0 of the polynomial of p of x is 1, we substitute 1 for x. And then we get 1 squared plus k minus 5 is equal to 0, giving us k is equal to 5 minus 1, and that equals 4. Now let's try to get a graphical sense of zeros of a polynomial. Essentially, whenever a polynomial crosses the x-axis and the number of times it crosses the x-axis, that gives us the number of zeros of that polynomial. For example, we have shown the linear case where y is equal to ax plus b. In that case, when we can see that the x-axis is being cut once, so in that case, it's showing that it has 1 0. In the quadratic case, and remember that a polynomial of degree n can have at utmost n zeros, but it's possible for them to have less than n zeros. A good example of that is the quadratic case, where in the first figure on the left, we show that it crosses the x-axis twice, and thus it has 2 zeros. But in the figure on the right, it doesn't touch the x-axis at all, so it has no zeros in this case. Therefore, it is important to remember that a polynomial of degree n can have at utmost n zeros, but they could very well have less than n zeros. In the third case, we show a cubic equation, ax cubed plus bx squared plus cx plus d, and as shown in the figure, it crosses the x-axis 3 times, so it has 3 0. Let's now find the relationship between zeros and coefficients of a polynomial. We will first take the case of a quadratic polynomial, which is generally given by ax squared plus bx plus c. In this case, let's say the zeros of that polynomial is alpha and beta. Therefore, alpha plus beta is given by minus b by a, and that equals negative of the coefficient of x in the equation ax squared plus bx plus c divided by the coefficient of x squared. And the product of the two zeros, alpha beta, equals c by a, which equals the constant term divided by the coefficient of the x squared in the quadratic polynomial. Now let's take a simple case. Suppose we have x squared minus 3x plus 2. Now the two factors for this, if we factorize it, is x minus 1 and x minus 2. So the two zeros, we equate that to 0, so we get the two zeros to be 1 and 2. And if we sum these two zeros, 1 and 2, we get 3. And as we can see from the equation x squared minus 3x plus 2, that equals minus b by a. Similarly, when we take the product of the two zeros, so it's 1 times 2, that gives us 2. And in the equation, that equals c by a, because c being 2 and a being 1. Let's now look at an example. Suppose we have to find the zeros of the quadratic polynomial and verify the relationship between the zero and the coefficient, and the quadratic polynomial given to us is 4s squared minus 4s plus 1. That we can factorize, and the two factors come out to be 2s minus 1 and 2s minus 1. So in this case, we have a double root. Now, the two zeros in this case, we equate them to 0, gives us s is equal to half and s is equal to half. Now, in this quadratic polynomial, we are given a is equal to 4, b is equal to minus 4, and c is equal to plus 1. Therefore, the sum of the two zeros is half plus half, and that is equal to 1. And the product is half times half, and that equals 1 by 4. In fact, if we want to verify the sum to be 1, then we just look at minus b over a in the equation 4s squared minus 4s plus 1, and which is given by minus of minus 4 divided by 4, and that gives us 4 divided by 4, and that equals 1. And the product is equal to c by a, which is c being 1 and a being 4, so we get 1 by 4. So hence we can verify that. Let's now find the relationship between zeros and coefficients of a cubic polynomial. Now in this case, we will have alpha, beta, and gamma are the zeros of the cubic polynomial. And remember that a cubic can have at most three zeros. So we'll take those three zeros as alpha, beta, and gamma. And let's say we are given a cubic polynomial of the form ax cubed plus bx squared plus cx plus d. And we are given that x minus alpha, x minus beta, and x minus gamma are the factors. So we can write fx is equal to k times x minus alpha times x minus beta times x minus gamma. Therefore, rearranging and putting in these factors, we show the relationship ax cubed plus bx squared plus cx plus d equals k times x cubed in parentheses x cubed minus alpha plus beta plus gamma x squared minus alpha beta plus beta gamma plus gamma alpha in parentheses times x minus alpha beta gamma. Therefore, we get alpha plus beta plus gamma is equal to minus b by a, and alpha beta plus beta gamma plus gamma alpha equal to c by a. Alpha, beta, gamma, the product equals minus d by a. And this is for the equation ax cubed plus bx squared plus cx plus d. So just remember that it is a negative coefficient of minus b by a. Then we have a positive c by a. And then we have the products of the three zeros minus d by a, which again is a negative. Now let's look at an example for a cubic polynomial. Verify that we are given zeros of the given cubic polynomials and then verify the relationship between the zero and its coefficient. we are given the zeros as 3, minus 1, and minus 1 by 3. And the polynomial is 3x cubed minus 5x squared minus 11x minus 3. So we plug in each of these values for x. So p of 3, as you can see, equals 81 minus 45 minus 33, that gives 0. P of minus 1 also gives us 0, and P of minus 1 by 3 also gives us 0. So this verifies the fact that these three are indeed the zeros of the polynomial. And now from the polynomial, we can see alpha is equal to 3, beta is equal to minus 1, and gamma is equal to minus 1 by 3. Therefore, alpha plus beta plus gamma in this case will give us 5 by 3, and which is in fact equal to minus b by a. If you compare it to the cubic polynomials, it's minus b by a. And alpha beta plus beta gamma plus gamma alpha gives us minus 11 by 3, which is equal to c by a in the given polynomial. And the product of the zeros, alpha beta gamma, equals 3 times minus 1 times minus 1 by 3, and that in fact gives us 1, and that's equivalent to minus d by a in the polynomial, because you can see that d has a value of minus 3, so minus 3 will give us 3, and a is equal to 3, so 3 divided by 3 will give us 1. Now let's look at a biquadratic polynomial, because the highest degree in this case is 4, and this is of the form fx is equal to ax to the power 4 plus bx cubed plus cx squared plus dx plus c. Now in this case, the sum of the zeros, alpha plus beta plus gamma plus delta, because remember this is a 4th degree polynomial, so we can have at most 4 zeros or 4 roots. So the sum of the roots is again given by minus b by a, and that is equal to minus negative of coefficient of x cubed by coefficient of x4, and the product of each of the two of these zeros, alpha beta plus beta gamma plus gamma delta plus alpha delta plus alpha gamma plus beta delta, is equal to c by a, and which is the coefficient of x squared to the coefficient of x raised to 4. And then the product of 3 of these zeros at a time, alpha beta gamma plus alpha beta delta plus beta gamma delta plus alpha gamma delta, is equal to minus d by a, which is the coefficient of x over the coefficient of x4. And finally, the product of all these zeros, alpha, beta, gamma, delta, is e by a, and that equals constant term over the coefficient of x4. And we can verify it. Look at the polynomial 2x to the power 4 plus 3x cubed plus 2x squared plus 5x plus 7. In this case, the sum of the zeros is given by minus 3 by 2, which is minus b by a. And similarly, the product of 2 at a time is given by 2 by 2, which is equal to 1. And the product of 3 at a time is given by minus 5 by 2, which is in fact the same as minus d by a. And the product of all these zeros, alpha, beta, gamma, delta, is given by 7 by 2. So now we have gone through the relationships between the zeros and the coefficients of polynomials, starting from quadratic, cubic, and biquadratic. Now let's come to the division algorithm, and it is in fact in principle the same as when we do the division algorithm in arithmetic. Basically what it says is the dividend equals divisor times quotient plus remainder. So for example, when we divide 7 by 3, 7 is the dividend and 3 is the divisor, and quotient is 2 and the remainder is 1. And that is typically written as 7 is equal to 3 times 2 plus 1. And again here 3 is the divisor and 2 is the quotient plus 1, and that is the remainder. The same principle is used when we are doing polynomials in the division algorithm. Let's now look at the following example, and where we will use the division algorithm. Divide the given polynomial by the given polynomial and also find the quotient and remainder. Now the polynomial given to us is a cubic one, which is 14x cubed minus 5x squared plus 9x minus 1. And the polynomial which we divide by gx is given by 2x minus 1. Now, by doing the long division, so we divide the cubic polynomial by 2x minus 1, we can see that we get the remainder 4. Now, in this case, the quotient comes out to be 7x squared plus x plus 5, and the remainder equals 4. And we can see that by the division algorithm, uh, if we write it in the form quotient times divisor plus remainder, and that equals gx qx plus rx. So in this case, in fact, when we multiply the terms out, we will get the the polynomial 14x cubed minus 5x squared plus 9x minus 1. Let's now look at the following example. Suppose we have to divide the given polynomial by the another given polynomial, and we have to find the quotient and remainder. So the polynomial given to us is fx is equal to 6x cubed plus 11x squared minus 39x plus 65. And the divisor in this case is going to be gx, which is x squared minus x plus 1. And when we do the long division method, uh, we it's very similar to the one we do in arithmetic. um, we get the remainder to be minus 38x plus 70. Now, if we want to again verify the division algorithm, we write the cubic polynomial, which in our case is 6x cubed plus 11x squared minus 39x plus 65, and we again write it in terms of the divisor and the quotient x square minus x plus 1, the product of those two, and 6x plus 5, and then plus the remainder minus 38x minus 60. And if we in fact expand the right side, we get 6x cubed plus 5x squared plus 6x squared plus 5x minus 6x minus 5 in parentheses, and then minus 38x minus 60. And in fact, that equals 6x cubed plus 11x squared minus 39x minus 65. And so in this case, we have got back the original polynomial, and hence we have verified the division algorithm.